One-way optical waveguide realized by edge modes of topological photonic crystals. Various types of crystals with regularly arranged atoms can be found in nature. The type and arrangement of their constituent elements mold the properties unique to each crystal. In many cases, it is the electrons that shape these properties. A periodic arrangement controls not only the electrons but also optical waves. The regular array for optical waves is called a photonic crystal. The unit structure of a photonic crystal is about 10,000 times larger than that of the crystal in nature. Because the wavelength of the electronic wave, that is, the de Broglie wavelength, is approximately an angstrom, while the wavelength of the optical wave is of the order of a micron. Thus, we gain control of the optical waves by matching to the size of the unit cells in the photonic crystals. This figure shows the electron micrographs of the photonic crystals used in this study with the unit structure of approximately 2 microns. Now, the 2016 Nobel Prize in Physics was awarded to David Dawes, Duncan Haldane, and Michael Kosterlitz for their theoretical discoveries of topological phase transitions and topological phases of matter. The topological features of matter lead to a variety of interesting physical manifestations. For example, in ordinary crystals, if an electron can flow to the right, it can also flow to the left. However, at the boundary between two types of crystals with different topological properties, only one wave flow is realized such that the electrons with spin upward always flow to the right and electrons with spin downward always flow to the left. Similarly, when two photonic crystals with different topological properties are pasted together, optical waves with right circular polarization or upward pseudospin will always flow to the right on the boundary, while those with the left circular polarization or downward pseudospin will always flow to the left. In this study, such a one-way optical waveguide was realized at the boundary between two kinds of photonic crystals. Specifically, the photonic crystals were designed by the finite element method and fabricated in a 0.4 micron thick silicon thin film using electron beam lithography. Their properties were verified by high-resolution infrared reflection measurements. The study of topological properties of optical waves is called topological photonics, and research in this field has been rapidly advancing in the recent years. This is because topological photonics is applicable to a wide wavelength range from microwaves to visible light. It is easy to try out new ideas because sample prototyping can be done by simply rewriting the CAD data for nanofabrication. Some properties that are difficult to measure with electrons can be measured with optical waves, and topological photonics is nearing the engineering applications.